If you flip a fair coin and it lands heads 5 times in a row, what are the odds the next flip is heads? Take a moment before you answer. There's a feeling that tends to arrive with a question like this. Something intuitive, almost below the level of words. It says, tails is due. 5 heads in a row is unusual. The universe must want to correct itself. Things need to balance out eventually. Some unseen hand must be about to nudge the system back toward the middle. That feeling is called the gambler's fallacy, and it is one of the oldest mistakes our species makes. The coin doesn't remember what it did last time. It has no history, no mechanism for balance, no awareness of the streak. The odds of the next flip landing heads are exactly what they have always been, 1 in 2, full stop. The 5 previous flips change nothing. Every toss is completely independent of every other toss, and yet the feeling doesn't go away. You can know this intellectually, completely, and the pull toward tails is still there, still humming underneath, still saying something has to correct. And tonight, we're going to find out exactly why. So settle in, get comfortable, maybe pull something warm a little closer. Tonight we're going to go through literally everything about probability, the history, how it actually works, and why your brain is so spectacularly bad at it. You don't have to stay awake for all of it. You don't have to try to remember anything. Just let the story come to you. This is a story that starts with animal bones thrown on dirt floors and ends with algorithms that can predict what you'll click on before you even know you want to click on it. It begins somewhere around 3,000 years before the Common Era, in a world that had no word for mathematics as we now use it, and it takes roughly 5,000 years to arrive at something you'd recognize from a textbook. 5,000 years, which already tells you something important about how strange and elusive this particular idea really was. Imagine you're standing in a room made of sun-dried mud bricks. The smell is dust and animal and something burning oil lamps. Maybe, or Jeddah Risen. It's roughly 3,000 years before the Common Era, somewhere in ancient Mesopotamia, in the region of what is now Iraq or Syria, and the person across from you is a priest. He reaches into a small clay bowl and draws out a handful of tiny bones. Not dice as you'd recognize them. These are astragali, the small tarsal bones from the ankle joint of a sheep or a goat, and the smooth ones are worn down by the hands of many generations before his. He shakes them in his cupped palms, making a sound like pebbles rolling together, and he casts them on the bare floor. They come to rest in a pattern. He leans forward and reads that pattern the way you might read a sentence. This is divination, and for a very long time, it was the primary human technology for dealing with randomness. The logic behind it was clean and internally consistent. The world has order. Things happen for reasons. Nothing is truly random. Because if the bones just fell with no meaning, what would that say about the gods, about fate, about justice? So when you face a question that the future holds, you consult the medium that connects the visible world to the invisible order. You cast the bones. You read what falls. You listen. The astragali had 4 usable landing positions, and different sides carried different meanings: favorable, unfavorable, very favorable, very unfavorable, depending on the tradition. Ancient Egyptian priests used similar techniques. So did people across what is now Iran, Turkey, the Indian subcontinent. Archaeological digs have found astragali in extraordinary abundance, in children's graves, as game pieces, as ritual objects, as tools of commerce, as toys. The same small bone wearing many different faces across thousands of miles of human civilization. And then the cubic die. The oldest 6-sided dice with pips arranged in roughly the modern pattern date to about 3,000 years before the Common Era, found in both Mesopotamia and South Asia, appearing, as far as we can tell, independently in both places around the same era. Some dice fragments found in ancient Egypt, maybe even older. The object, the impulse behind it, the practice of casting something small and uncertain to reveal information, these appear everywhere, across every major ancient civilization we know of, with a persistence that suggests something very deep. Here's the thing I keep coming back to. This isn't just a story about humans enjoying games, though clearly they did, and clearly they still do. It's a story about what randomness meant, because in the ancient world, randomness wasn't noise, it wasn't error, it wasn't something to be minimized or corrected. It was a direct channel to divine intention. The pattern the bones made when they landed wasn't an accident. It was a message, and that framing randomness as sacred, as meaningful, as the voice of something larger turns out to be one of the most durable ideas in human history. The Greeks, of all people, seem like the civilization most likely to have broken this pattern. Picture Athens in the 4th century before the Common Era. This is a culture that has built formal proof from scratch, the idea that you can start with axioms and reason your way to certain conclusions, step by step, with no room for error. Euclid's geometry, much of which was assembled during this period, is so rigorous that it served as the gold standard of mathematical reasoning for 20 centuries. These are people who proved that the square root of 2 can be expressed as a fraction, who separated logic from rhetoric, who built the philosophical foundations that the scientific revolution would eventually stand on. Aristotle, who was born around 384 years before the Common Era and spent most of his intellectual life in Athens and Macedonia, came closer than almost anyone in the ancient world to grasping the outlines of probability. He made a careful distinction between events that happen by necessity and things that always occur the same way, and events that happen by accident, things that are contingent, that could have gone differently. He thought seriously about chance and coincidence, about why some things seem to just happen. He was circling something real, but he never quantified it. And that's the historical puzzle that gets me every time. Not just Aristotle, nobody in the ancient Greek or Roman world ever sat down and computed a probability. Not once, not a fraction, not a ratio, not even a rough estimate. They had the arithmetic to do it. The question of how many ways you can roll a given number on 2 dice is a problem you can solve using the reasoning they already possessed. The Romans were gambling furiously the entire time. Soldiers played with knucklebones in camp between campaigns. Julius Caesar crossed the Rubicon with the phrase, "The die is cast," which tells you exactly how thoroughly dice had embedded themselves into the Roman imagination as a metaphor for fateful, irreversible choices. The Emperor Augustus, by multiple accounts, couldn't resist a game. We have letters in his own hand describing his dice sessions, his wins and losses, his wry acknowledgement that he wasn't very good. Gambling was everywhere in the Roman world. It was so pervasive that Roman law repeatedly tried to restrict it, which mostly didn't work. And still, no probability theory. It's worth pausing here to notice that the Indian philosophical tradition was approaching the same questions from a completely different angle. The Hindu concept of karma doesn't dismiss what looks like randomness, but it reframes it entirely. What appears to be chance from the outside is the working out of a vast moral accounting system. Actions from this life and previous lives, creating conditions that ripple forward through time. Under that framework, there's no true accident. Every outcome has causes, even if those causes stretch back further than any human eye can see. Buddhist thought offers something similar in the doctrine of dependent origination, the idea that every phenomenon arises in dependence on conditions, that nothing occurs without cause, that the web of causes and conditions is so vast and intricate that it can appear to be random without actually being so. These are not naive positions. There's genuine philosophical depth in the idea that what looks random to us reflects an order we can't fully perceive. And the interesting thing is that both traditions arrive at essentially the same practical conclusion that the ancient Western world arrived at. Randomness belongs to a larger order. It is not something you calculate. It is something you navigate, something you read, something you receive. Here's the part that blows my mind a little. Though we should not be too quick to feel superior to the ancient priests with their bones and their divine consultations, because your brain is doing something remarkably similar right now without asking your permission. Human brains are pattern recognition machines. That's not a criticism, it is the most important thing about us. We are the species that survived and multiplied and eventually built cities, partly because we are extraordinarily good at detecting structure in noisy environments. The rustle in the tall grass might be wind. It might be a lion. The brain that treats both possibilities as equally likely gets eaten once. The brain that leans toward assume lion, act accordingly survives to have children who have the same kind of brain over vast stretches of evolutionary time. The bias toward seeing patterns, toward assuming that apparent signals are real signals, is selected for very hard. Psychologists call this apophenia, the tendency to perceive meaningful connections between unrelated things. And in the world our brains were built for, apophenia is almost never costly. In a complex biological environment, apparent patterns usually are patterns. The streak of bad weather, the unusual behavior of animals before a storm, The cluster of animal tracks near the waterhole, these are information. Treating them as meaningful is correct. But apply that same system to coin flips and something breaks. The gambler's fallacy works like this. Your pattern recognition system notices the streak of 5 heads. It flags this as unusual, which is correct. It is somewhat unusual. And then it predicts a correction because in almost every real-world context where streaks occur, they do eventually correct. 5 rainy days makes the 6th more likely to be sunny. In many climates, unusual runs of anything tend to revert toward the average eventually. Your brain has learned this rule from a world where it is generally true. It's just not true for fair coin flips. Because the coin exists outside of context. It has no weather. It has no memory. It has no tendency to revert. Each flip really is completely isolated from every other flip, but your brain can't feel that isolation. It feels the streak, and it expects the correction, and no amount of knowing the statistics entirely at the intellectual level will make that feeling go away. The mirror image of this is something called the hot hand illusion. In basketball and in many other contexts, players and fans and coaches deeply believe that a shooter who has made several shots in a row is more likely to make the next one. They have a hot hand. There was a famous paper in the early 1980s by the psychologists Gilovich, Vallone, and Tversky that looked at actual shooting data from professional basketball and concluded that the hot hand was a pure cognitive illusion, that there was no statistical evidence for it at all, that past makes had essentially no predictive value for the next shot. This made a lot of basketball coaches extremely unhappy. There was a fascinating academic back and forth for decades, and more recent research suggests there may be a small, real effect under specific conditions. But here's what's interesting either way. The subjective experience of momentum, the sense that a shooter is on fire, is vastly more vivid and more compelling than any underlying statistical signal. We perceive patterns as much larger and much more meaningful than they actually are. Just think about what that implies for a moment. You have a cognitive system designed at evolutionary depth to find patterns everywhere, to give them meaning, to act on them. And that system was built in an environment where genuine randomness was essentially absent, where almost everything that looked like a pattern was a pattern. Then you put that cognitive system in a world that contains true randomness in gambling, in financial markets, in complex systems, and it keeps doing what it was built to do. It finds the pattern, it assigns the meaning, it hears the message. Exactly like the priest reading the bones. And here's what I find genuinely astonishing about all of this. For roughly 4,000 years, humans rolled dice without ever doing the math. They built empires and irrigation systems and astronomical calendars of extraordinary precision. They invented geometry and formal logic and the beginnings of what we'd now call physics. They proved that the square root of 2 is irrational and that there are infinitely many prime numbers. They developed philosophical traditions that are still alive today. But not one person in the ancient world, not one Greek geometer, not one Roman administrator, not one Babylonian astronomer, not one Indian mathematician ever sat down and calculated the odds of rolling a 6. Let that sit for a second. The arithmetic is trivial. One side out of 6 possible sides. A child could work it out today. With the mathematics that already existed in Aristotle's time, the calculation would take moments. It isn't that the question was hard. The question is absurdly easy. The question just never got asked. And that absence, that 4,000-year silence, is one of the most fascinating gaps in the entire history of ideas. Not the failure to answer a difficult question, but the failure to ask an obvious one. Something about the way randomness was framed as sacred, as meaningful, as a message from a larger order made the mathematical approach essentially unthinkable. The dice were a channel, not a mechanism, and you don't calculate a channel. You read it. It took a very specific set of circumstances to finally break that silence. A professional gambler with a problem he couldn't solve. A French nobleman with too much money and a losing streak he couldn't explain. And a mathematician who happened to be exactly the right person to write to. The answer came not in a formal treatise or a public lecture, but in a series of private letters, written over the course of a single summer, discussing a gambling problem so specific and so mundane, it seems almost embarrassing as the seed of a major branch of mathematics. The question was simply this: if two players are in the middle of a game of chance, and the game gets interrupted before anyone wins, how do you fairly divide the pot? That question, passed back and forth between Blaise Pascal and Pierre de Fermat in the summer of 1654, became the founding correspondence of probability theory. Neither of them fully understood what they were building, and the letters were never meant to be seen by anyone else, which is where we're going next. The letters began in the summer of 1654, and they started, as so many important things do, with someone losing money. Antoine Gombeau was his name. He called himself the Chevalier de Méret, the Knight of Méret, except he wasn't actually a chevalier. He had no hereditary claim to the rank. He just liked the sound of it and started using it, which tells you something about the man before you've heard a single word he said. Gombeau was born around 1607 in Paris, a fixture of the salons, those candlelit, wine-scented gatherings where Parisian intellectuals and aristocrats and ambitious social climbers went to argue about ideas. He was witty, opinionated, genuinely interested in mathematics, and he gambled, not as a vice, exactly more as a vocation. He developed his own intuitions about games of chance over years at the table, and when he ran into a problem, those intuitions couldn't untangle. It nagged at him, and eventually, because he knew Blaise Pascal, he wrote a letter. The problem he brought to Pascal is now called the problem of points. And here's the thing, when you first hear it, it sounds so simple you wonder why anyone had to think about it at all. Imagine two players sitting down to a dice game. First 1 to 10 wins takes the whole pot. One player reaches 7 wins. The other has 5. The game gets interrupted. It can't be finished. How do you fairly divide the money? The obvious instinct is to split it proportionally to rounds won, but that's not quite right. and Gombo sensed it without being able to explain why. What matters isn't how many rounds have happened. What matters is what would have happened, how many more rounds each player needed, and how likely each of them was to actually win the rest of the game. The trailing player would have needed 5 more wins. The leader needed only 3. Their situations are genuinely different. But how different exactly? This question, which sounds like a minor accounting problem, had been sitting unanswered for about 200 years. The problem is harder than it looks because it requires you to reason about a future that never occurred, to assign value to events that didn't take place. That is, it requires probability. Now, Blaise Pascal, let me tell you about Blaise Pascal, because this is one of my favorite characters in the entire history of mathematics, and not just for what he built. Pascal was born in 1623 in Clermont-Ferrand, France. His father, Etienne, was a tax official and amateur mathematician who took his children's education with an almost alarming seriousness. When Pascal was around 7, Etienne decided the boy shouldn't study mathematics, yet languages first, and locked up all the math books in the house. Pascal was 12 when he started doing geometry on his own, working from scratch on the floor with a piece of chalk, inventing his own names for things because he didn't have the vocabulary. A round was a circle, a bar was a line, without books, without being taught. He rederived the first 32 theorems of Euclid's Elements. His father found him doing this and reportedly wept. He was 12. By 16, he'd written a major theorem about conic sections, still called Pascal's theorem today. By 19, he'd built a mechanical adding machine. By 25, he was doing atmospheric pressure experiments that helped found the science of barometry. And then, at 31, he sat down with a gambling question from a man who liked to pretend he was a knight, and in working through it, helped construct something that would eventually reshape how the entire world makes decisions under uncertainty. When Gombo brought the problem of points, Pascal didn't try to solve it alone. He wrote to Pierre de Fermat. Fermat. There's a name. Pierre de Fermat was born in 1601 near Toulouse, and by profession he was a lawyer. He did mathematics in what we'd now call his spare time, which is sort of like saying he wrote the Principia as a hobby, extraordinary work, produced as a side project. He had methods for finding maxima and minima that are essentially pre-calculus, a number theory that mathematicians are still studying today, and this endearing, infuriating habit of claiming he had proofs he never wrote down. The most famous, a note in the margin of a book by Diophantus. Reading, I have discovered a truly marvelous proof of this proposition, which this margin is too narrow to contain. That claim, Fermat's last theorem, went unproven for 358 years. When Andrew Wiles finally proved it in 1995, his proof required mathematical techniques that didn't exist in Fermat's time. That margin note has been quietly haunting people for 4 centuries. Anyway, in the summer of 1654, these two men began writing to each other about gambling. The exchange between Pascal and Fermat over that summer is one of the most celebrated correspondences in the history of mathematics. A dozen letters or so, back and forth. dense with calculations and polite corrections. Neither was trying to found a new discipline. They were trying to solve a specific puzzle. But the methods they developed turned out to be general applicable to any situation where you needed to reason about uncertain futures. What they were working out, letter by letter, was the concept of expected value. Here's the intuitive version. You're about to play a simple game. Flip a coin. Heads, you win 3 coins. Tails, you win nothing. How much should you pay for the right to play? Your intuition says, half the time I get 3, half the time nothing. So, on average, 1.5. And that intuition is exactly right. 1.5 coins is the expected value what you'd average if you played 1,000 times. But here's what makes this subtle. The expected value exists before a single coin is flipped, even if the game is interrupted, even if the outcome never arrives. It's the mathematical way of asking, given everything I know about how this unfolds, what is a fair price right now? Applied to the problem of points, forget what's happened so far. Look at all the possible ways the game could finish from this moment forward. Calculate the probability of each outcome and weight each player's share accordingly. The player who would win in more of the possible futures deserves more of the pot, not because they will definitely win, but because the space of possibilities tilts in their favor. This was genuinely new thinking. Before Pascal and Fermat, chance was just chance. You could feel that some outcomes were more likely than others, but there was no formal machinery for attaching numbers to uncertainty about the future. These letters created that machinery. The news spread through the informal network of European mathematical correspondence, the pre-internet academic grapevine, conducted entirely by letter. Within a few years, it reached a young Dutch polymath named Christian Huygens was, by any measure, one of the most remarkable minds of his century, inventor of the pendulum clock, discoverer of Saturn's rings and its largest moon, major contributor to optics and wave theory. When he heard about the Pascal Fermat correspondence through second-hand accounts, he worked out the theory of probability himself from scratch. In 1657, he published De Ratiocinis in Ludo Allee on reasoning in games of chance, the first systematic published textbook on probability for an entire generation of readers. It was simply how you learned the subject until a man from Basel went much further. Jacob Bernoulli was born in 1655, part of one of the most staggering intellectual dynasties in mathematical history. The Bernoullis of Basel produced at least 8 significant mathematicians across 3 generations, which is either extraordinarily impressive or mildly exhausting depending on your perspective. Jacob read Huygens's book and spent the next 20 years working on what he believed was its proper completion. He called it the ars conjectandi, the art of conjecture. He never finished it. Bernoulli died in 1705, and the ars conjectandi was published posthumously in 1713, 8 years after his death, by his nephew Nicolaus. Even as published, it was incomplete. 2 decades of work left open. There's something about that I keep returning to. The foundational text of probability theory was left unfinished, published after the author's death by a relative who had to figure out what to do with the manuscript. That is not how triumphant chapters of scientific history usually read, but that is how this one actually went. The centerpiece of the Ars Conjectandi is what we now call the law of large numbers. And this idea is worth sitting with. You have a coin and you don't know if it's fair. You flip it once heads, tells you almost nothing. 10 times, maybe 7 heads, 3 tails, 100 flips, 1,000, 10,000. And here's what Bernoulli proved. As the number of flips grows, the proportion of heads will converge toward the true underlying probability, whatever that actually is, with a certainty that approaches absolute. The chaos of individual outcomes averages out. Given enough patience, the noise becomes signal. The law of large numbers is the universe's promise that repetition reveals truth. It's why casinos always win over time, even though individual gamblers sometimes get lucky. It's why insurance companies can price risk without knowing which specific customers will file claims. It's the mathematical guarantee that careful observation at large enough scale tells you something real about the world, not just about what happened to happen, but about what tends to happen. And now I have to come back to Pascal, because Pascal's story takes a turn that I think is one of the most haunting pivots in the history of ideas. While Pascal and Fermat were exchanging those probability letters in the summer of 1654, Pascal was also going through something else entirely. He'd been spending time in Jansenist circles, a Reformed Catholic movement that emphasized human sinfulness and divine grace, and his faith had become restless, contested with himself in ways the mathematics couldn't resolve. Then, in November of 1654, something happened on a bridge over the Seine. Pascal was in a carriage with friends. The horses bolted. The carriage lurched toward the edge of the bridge. The front horses actually went over, pulling the carriage partway with them. The harness traces broke. The carriage stopped, hanging halfway over the water. Pascal survived, but only just. That night, he had an experience he described as a mystical vision. 2 hours of fire. He wrote, certitude, certitude, feeling, joy, peace. He wrote down what he'd felt the presence of God, direct and overwhelming, and utterly unlike anything the intellect could reach. He wrote it on a piece of parchment, copied it onto vellum, and then, and this is the detail that stops me every time, he sewed both pieces into the lining of his coat. He wore that coat for the rest of his life. He never showed anyone what was written there. His servants found the hidden parchment after he died by feeling something stiff in the fabric. He had worn it secretly against his body for 8 years. That piece of paper is now called the Memorial, and it sits in the Bibliothèque Nationale de France. Pascal did almost no mathematics for the remaining 8 years of his life. He wrote theology, philosophy, religious apologetics, working on a large defense of Christianity he never finished, fragments of which survived in Stes Pensées. And in those fragments you find something that reframes everything that came before. Pascal had taken the mathematical tools he'd helped build and pointed them at the question he now cared about most. His argument goes like this: you don't know whether God exists. You can't prove it either way, but you have to live, and in living, you are placing a wager. If God doesn't exist and you live as though God does, you lose something finite, some pleasures, some freedoms. If God does exist and you live as though God doesn't, you lose infinitely. The expected cost of disbelief, weighted even by a small probability of God existing, is boundless. The expected cost of belief is finite. Therefore, the only rational wager is belief. This is Pascal's wager. Whatever you think of the theology and philosophers have spent centuries pointing out genuine problems with it, the structure of the argument is the foundation of decision theory. Identify possible outcomes, assign probabilities, calculate expected values, choose accordingly. That structure is how actuaries price risk, how doctors weigh uncertain treatment options, how engineers calculate acceptable probability of failure. Pascal used it to argue himself toward God, but the tool he was using is everywhere in modern life. And here is the irony that sits at the center of this story. The man who helped prove that uncertain futures could be given numbers, who helped establish that rational action under uncertainty meant calculating expected values and following where the math led, used that very mathematics to argue that he should stop trusting mathematics and surrender to faith instead. He calculated his way out of calculation. He used probability to reach a conclusion that probability on its own could never provide. Pascal died in 1662. He was 39 years old. He'd been ill for most of his adult life, persistent headaches, pain, symptoms that modern physicians have attributed to everything from a brain tumor to conditions that simply can't be diagnosed across 3.5 centuries. He lived in near constant discomfort and still produced, in the time he had, a body of work: the calculator, the theorem, the probability letters, the physics, the theology that most people couldn't accumulate in 3 long, healthy lifetimes. Think about what was in the lining of that coat. Not a formula, not a theorem, a description of 2 hours of fire and the feeling of something the equations couldn't touch. The Pascal of summer 1654 sharp, precise, working through the mathematics of interrupted games, and the Pascal of that November night, pressing a secret note about fire and joy into the lining of his coat and keeping it there for the rest of his short life. He crossed a threshold that summer and autumn he never came back from. The man who helped tame chance with mathematics then surrendered to it entirely. And so, by the early 1700s, mathematicians had a working theory of chance for dice, for quines, for interrupted games, for the long-run behavior of repeated events. They could assign numbers to uncertainty. They could calculate fair prices for futures that might never arrive. They could prove that observation, given enough patience, converges on truth. But the real world is not a casino. The real world doesn't hand you a game with known rules and ask you to calculate the odds. The real world gives you outcomes you didn't design. data that arrives without instructions, effects with no label saying what caused them, and the question that would haunt the next century of mathematical thought was this: can you run probability backwards? Forward probability is what Pascal and Fermat built. Given a known game with known rules, what are the odds? But can you go the other direction? Can you start with what you've actually observed with the data in front of you and use it to reason backwards toward the world that generated it? Not predict the future from what you know, but infer the past from what you see? That question has a name, and the man most associated with it was an English minister who died before he could publish his most important work, and whose ideas sat quietly in a drawer for years after he was gone. His name was Thomas Bayes. And honestly, the story of how his most important idea reached the world is almost melancholy in its quietness. Picture a small town called Tunbridge Wells in England, sometime in the middle of the 1700s. It's a spa town, known mostly for its mineral springs and its genteel visitors who come to take the waters. In that town, in a stone church, there is a Presbyterian minister named Thomas Bayes, mild, scholarly, not particularly famous. He was born around 1701, ordained as a minister, and spent most of his adult life giving sermons and quietly doing mathematics on the side, the way some people do crossword puzzles or tend gardens. He published almost nothing mathematical in his lifetime. One small paper on calculus, defending Isaac Newton from a critic. That's essentially it. Whatever else he was working on, he kept private. And then, in 1761, he died. Among his papers, his friend Richard Price found something, a manuscript, handwritten, untitled, never submitted anywhere. Price read it and understood immediately what he was looking at. He edited it, wrote a preface, and sent it to the Royal Society in London. In 1763, 2 years after Bayes' death, it was published in the Philosophical Transactions of the Royal Society. Bayes never knew his idea had been heard by anyone. I find that detail quietly extraordinary. Not the mathematics, just that a man writes something down, puts it away, and never tells the world. And the world finds out anyway, 2 years after he's gone. The paper was called, in the elaborate style of its era, an essay towards solving a problem in the doctrine of chances. And what it contained was a method for doing something no one had figured out how to do rigorously before. A method for running probability backwards. Here's what I mean by that. Forward probability is the direction that feels natural. You have a fair coin. You flip it 10 times. What's the probability you get exactly 7 heads? You have a bag with 3 red balls and 2 blue balls. You pull one out without looking. What are the odds it's red? In each case, you know the mechanism generating the outcomes, and you're asking what to expect. Forward, cause to effect. Bayes' paper asked the reverse. What if you already have the outcomes? What if you're looking at the data, the effects, and you want to reason backwards toward what might have caused them? This is the question that the entire field of statistical inference is built around. And the answer Bayes worked out is, at its heart, surprisingly intuitive once you see it through the right lens. Think of it this way. Imagine you have a dial, a belief dial. It goes from 0 to 100, representing how confident you are that something is true. 0 means completely certain it's false. 100 means completely certain it's true. Most beliefs sit somewhere in the middle. Bayes' theorem says when new evidence arrives, the dial turns. How much it turns depends on two things. First, how strongly does the new evidence favor one explanation over another? If the evidence is very unlikely to occur unless your hypothesis is true, the dial turns a lot. If the evidence could plausibly arise from many different explanations, it barely moves. Second, where did the dial start? What was your belief before the evidence arrived? Bayes called this the prior. The prior is everything you already knew or reasonably believed before you saw the new data. And that second piece, the prior, is what makes Bayesian reasoning so different from how most people naturally think. The temptation when you get surprising evidence is to focus entirely on the new information and forget what was already known. Bayes says you cannot do that rationally. The prior always matters. Evidence does not exist in a vacuum. Let me make this real with an example, because this is the one that genuinely changes how people think about probability when they first encounter it. Imagine a disease that affects 1 in 1,000 people in the general population. Not common at all. 1 in 1,000. Now, imagine a test for that disease that is 99% accurate. If you have the disease, the test says positive 99% of the time. If you don't have it, the test says negative 99% of the time. Excellent test. By any measure, you take the test, it comes back positive. How worried should you be? Most people's gut says, very worried. 99% accurate. Positive result. That sounds like almost certain bad news. The actual answer is way less worried than you think. Here's why. Imagine 10,000 people all take this test. About 10 of them actually have the disease. 1 in 1,000. The test correctly identifies 9 of those 10 as positive. 1 slips through as a false negative. But the 9,990 healthy people also take the test. And 1% of them, about 100, get false positives. So across the 10,000 people, about 109 test positive. And of those 109, only 9 are actually sick. That's less than 9%. If you test positive for this disease, the probability you're actually sick is less than 9%, not 99%, less than 9. 9. I think about that gap a lot. The accuracy of the test is only half the story. The prior, the base rate, the rarity of the disease, it's still there doing its quiet, invisible work no matter what the test says. That's not a detail. That's the whole point. This phenomenon has a name, the base rate fallacy, and it turns up everywhere. that important decisions get made under uncertainty. In medical diagnosis, in legal evidence, in security screening, in machine learning systems that flag anomalies, the signal tells you something, but the prior tells you how loud to actually hear it. Now let's talk about the Frenchman who took Bayes' quiet insight and turned it into something vast. Pierre Simon Laplace was born in 1749 in Normandy, the son of a farmer, or possibly a cider merchant. Records unclear, and Laplace grew increasingly vague about his origins as his fame grew. What is not ambiguous, extraordinarily intelligent, extraordinarily ambitious, and extraordinarily skilled at surviving whatever political climate surrounded him. He lived through the French Revolution, the Terror, the rise of Napoleon, the Restoration. He adjusted as needed. Napoleon himself is supposed to have asked Laplace once why his monumental work on the mechanics of the solar system made no mention of God. Laplace reportedly replied, "I had no need of that hypothesis. It's one of the great lines in the history of science. And whether or not it happened exactly as reported, it captures the man perfectly. No patience for anything mathematically unnecessary." Laplace independently developed the ideas in Bayes' paper, apparently without knowing Bayes' work existed, and then took them far beyond anything Bayes had attempted. He used probability to attack problems in astronomy. He calculated the masses of planets. He estimated the probability that the sun would rise tomorrow, a question that sounds absurd until you realize it's actually a serious exercise in reasoning from observed frequencies. He applied Bayesian reasoning to legal evidence, to demographic records, to experimental data in physics, and Laplace arrived at a philosophy of probability that is, I think, one of the most elegant ideas in all of mathematics. De Laplace, probability was not a property of the world. It was a measure of knowledge and of ignorance. When you say a coin has a 50% chance of landing heads, you are not saying something about the coin. You are saying something about you, about what you know and what you don't. The coin will land exactly where the physics of that specific moment dictates, but you don't have access to all that physics. So you reason under uncertainty, and probability is the mathematical language for doing that honestly. That philosophy, probability as a measure of belief, updated by evidence, is called Bayesian probability. It is beautiful, coherent, and, as we're about to see, surprisingly controversial. But first, let me take a short detour through a puzzle that illustrates the strangeness of Bayesian reasoning in a way that is genuinely infuriating the first time you meet it. The Monty Hall problem. You are on a game show. 3 doors. Behind one, a car. Behind the other 2, goats. You want the car. You pick door number 1. The host, Monty Hall, who knows where the car is, opens another door, say door number 3. To reveal a goat, he offers you a choice. Stick with door number 1 or switch to door number 2. What should you do? Almost everyone says it doesn't matter. 2 doors left. One has the car, so it's 50-50, right? Wrong? You should always switch. Switching doubles your probability of winning. The Monty Hall problem is what happens when your gut feeling and actual mathematics have a head-on collision, and mathematics wins every single time. Here's the logic. When you picked door number 1, you had a 1 in 3 chance of being right, 2 in 3 chance the car was behind one of the other two. Monty will never open the car door and will never open your door. He picks a non-car door from the two you didn't choose. So his reveal doesn't redistribute the probability equally. That 2 in 3 was already on those two doors. And when one is eliminated, it collapses onto door number 2. Door number 2 now has a 2 in 3 chance. Door number 1 still has 1 in 3. When this puzzle was published in a magazine column in 1990, the columnist who gave the correct answer received thousands of letters insisting she was wrong. Many came from people with advanced degrees in mathematics and statistics. I love this detail. Actually, not because it's funny, but because it proves the point. The brain just resists this one. Our intuitions about probability were built for navigating social environments and physical risks, not for elegant conditional logic. Bayesian reasoning is something you have to learn and sometimes relearn. There's a related result that's worth a quick mention: the birthday problem. How many people in a room before there's a better than 50-50 chance? Two of them share a birthday. Most people guess around 180. The answer is 23. With just 23 people, the odds pass 50%. With 50, they hit 97. The reason is that you're not asking about any one person's birthday. You're asking about any pair, and the number of possible pairs grows much faster than the number of people. 23 people have 253 distinct pairs. The math doesn't care that the answer surprises you. It just works out. And once you know it, I find that birthday coincidences stop being remarkable, which is either delightful or slightly sad, depending on how you feel about the slow erosion of wonder by mathematics. Now, the deeper story, because Bayesian probability didn't just produce clever puzzles, it set off one of the great intellectual wars in the history of science. For most of the 20th century, a fracture ran through the field of statistics, a deep, sometimes personal disagreement about what probability fundamentally is. On one side, the Bayesians, probability is a degree of belief, updated rationally when evidence arrives. Start with a prior, observe the data, arrive at a posterior, and that posterior becomes your new prior for the next round. Coherent, philosophically clean. On the other side, the frequentist position is that probability should not be about belief at all. Probability means the long-run frequency of an event over many repeated identical trials, not what you believe on a given morning, what actually happens repeatedly under reproducible conditions. The man most associated with frequentist statistics was Ronald Fisher, born in 1890, brilliant and combative in roughly equal measure. Fisher essentially invented the toolkit that most scientists still use today: p-values, null hypothesis testing, significance levels, analysis of variance, and he despised Bayesian methods with a sustained intensity that goes beyond professional disagreement. He found the whole apparatus of priors and posteriors philosophically contaminated, unscientific. Fisher was influential enough that for a long stretch of the 20th century, Bayesian methods were treated as slightly disreputable, not exactly wrong, just not the approach that serious scientists should use. On the Bayesian side, quietly and persistently, was Harold Jeffreys. Jeffreys was a geophysicist and mathematician at Cambridge, born the year after Fisher, and he spent much of his career systematically building out the Bayesian framework, defending it philosophically, laying its foundations carefully. He and Fisher were almost exact contemporaries, working at the same university for decades, and they disagreed about as fundamentally as two people working on the same subject can possibly disagree. Jeffreys was largely ignored. Fisher's framework dominated science for a generation, and I find something a little mournful about that. The way Jeffreys kept building the thing carefully for decades while the field mostly looked elsewhere. Then something shifted. By the 1980s and 90s, as computers became powerful enough to actually run the calculations that Bayesian methods require, the Bayesian framework staged a comeback. It turned out to be extraordinarily well suited to exactly the problems that were becoming central to technology: machine learning, spam filtering, medical diagnosis systems, recommendation engines. All of them are underneath Bayesian engines. They start with priors about the world. They observe data. They update. The dial turns. The filter that keeps junk email out of your inbox is, at its mathematical heart, a Bayesian classifier. It has beliefs about which words tend to appear in spam versus legitimate mail. And every time you mark something as junk or pull something back from the spam folder, you're feeding it new evidence. The model updates over time. It converges toward a pretty accurate picture of what you want to read. Bayes' Quiet Theorem, written by a minister in Tunbridge Wells and left unpublished in a drawer, is running right now on servers all over the world. And I genuinely love that as a fact about how history works. The idea didn't need him to champion it. It just needed to be true. And here's what I find genuinely profound about Bayes' theorem. The thing that goes beyond just a formula for combining probabilities. It means that certainty, absolute total certainty, is mathematically irrational. If your prior probability for something is exactly zero, no amount of evidence can ever change your mind. Multiply by any update factor you like. Zero stays zero. If your prior is exactly one, the same problem, nothing can shift it. The formula only works for values strictly between 0 and 1, which means that to reason correctly, to be a good Bayesian reasoner, you have to begin by admitting that you might be wrong about everything. You have to leave a crack in the door, not a wide crack, not if you're quite confident. You can start with a probability of 1 in a trillion if you like, but the crack has to exist, because if it doesn't, evidence cannot reach you. There's something almost devotional about that. The mathematics of rational belief begins not with certainty, but with the admission that certainty is always, to some degree, premature. To close your mind completely is not conviction, it's a failure of the algorithm. The framework doesn't tell you what to believe, it tells you how to update your beliefs as you encounter the world. Start somewhere reasonable, revise honestly, let evidence accumulate, and given enough evidence, two people who began in very different places will eventually converge toward the same beliefs, because the evidence is the evidence, and it points where it points. Thomas Bayes, working alone in Tunbridge Wells, left that behind in a drawer. Richard Price found it and sent it into the world. And Laplace, the man who survived everything, built it into a system grand enough to weigh the planets. But probability wasn't content to stay philosophical. In the late 1800s and early 1900s, a generation of mathematicians grew restless. The debates between frequentists and Bayesians were important. Yes, but there was a deeper problem sitting underneath both of them. Neither side had fully answered what probability actually is in a rigorous mathematical sense. What are the rules it must obey? Can you derive the whole subject from a small set of axioms, the way geometry grows from a handful of postulates? A group of mathematicians decided to build the whole thing from scratch, to give probability a foundation as rigorous as geometry, as solid as logic itself. And the person who finally did it was a Soviet mathematician working under Stalin, who managed to build one of the most elegant mathematical frameworks in history while the world around him was falling apart. So, let me tell you about Andrei Kolmogorov. He was born in 1903 inches, a small town in central Russia, and his life began with loss. His mother died giving birth to him. His father was killed years later in the Civil War. He was raised by his aunt, Vera Yakovlevna, a quiet, devoted woman who essentially built her life around this strange, brilliant boy who had arrived in the world, having already cost someone else theirs. Just hold that for a moment. The man who would build the mathematical foundation of all modern probability was himself, from his very first second, a kind of probability event, a life that so easily might not have continued. He arrived at Moscow State University as a teenager, and it became clear almost immediately that he thought about mathematics differently from other students. He wasn't just talented at solving problems. He wanted to know what the problems were built on. What were the deepest rules? What was the smallest possible set of assumptions from which everything else could follow? And in 1933, when he was 30 years old, working under Stalin's shadow in a Moscow that was growing more dangerous by the year, he published a book in German because that was still the language of serious mathematics. The title translates roughly as Foundations of the Theory of Probability. It is not a long book. You could read the whole thing in an afternoon. And in it, Kolmogorov laid down three axioms, three rules from which the entire theory of probability can be built. Three axioms. That's it. And I want to sit with that before we go any further. For 300 years, probability had been accumulating results. Bernoulli's law of large numbers, the Moivre-Bell curve, Bayes' theorem, Laplace's celestial mechanics, but none of it had a shared foundation. Different mathematicians started from different assumptions, argued past each other, disagreed on what probability even was as a mathematical object. Kolmogorov said, "Here are three statements. If you accept these three statements, everything else follows. The first, probabilities are never negative. You cannot have a minus 30% chance of rain. Numbers that represent probability start at zero and go upward from there. The second, the probability of something certain is 1. If you're rolling a die and you want the probability that it shows any number at all, that probability is 1. Certainty is the ceiling. The third, if two events can't both happen at the same time, a coin showing heads and tails on the same flip, then the probability of either one happening is simply the sum of their individual probabilities. 1/2 plus 1/2 equals 1. You just add 3 rows, none longer than a sentence. And from just these three, Kolmogorov and the mathematicians who followed him derived the entire structure of modern probability theory. Every formula, every theorem, every result. Kolmogorov's axioms are to probability what Euclid's postulates are to geometry, a handful of simple starting points from which the entire universe of the subject unfolds. Euclid had 5 statements about points and lines. Kolmogorov had 3 statements about numbers. From each, a whole world, which means take a moment and really feel what that implies. The framework your insurance company uses to price your policy, and the framework NASA uses to calculate trajectory confidence intervals, and the framework your spam filter uses to decide what you don't want to read, they are all underneath the same 3 sentences written in a Soviet apartment in 1933. Now, before we get to how those axioms connect to the most beautiful results in all of this, let me take you to a peculiar wooden device built by a Victorian gentleman with extraordinary facial hair. Francis Galton was born in 1822 inches, Birmingham, a cousin of Charles Darwin, with the kind of restless, omnivorous mind that only seems to thrive in certain eras. He worked on statistics, meteorology, psychology, geography. He invented fingerprinting as an identification method. He coined the phrase nature versus nurture. And in 1889, he built something he called a quincunx, which today most people know as the bean machine or the Galton board. Picture it like this: a vertical board with rows of pegs. You drop a small ball at the top. It hits the first peg and bounces left or right, roughly equal odds either way. Then the next row, left or right again, row after row, until it drops into a collection bin at the bottom. Each individual ball follows a completely unpredictable path. You cannot know, watching any single ball begin its journey, where it will end up, but drop hundreds of balls and watch where they accumulate. They form a shape. The bins in the middle fill up the most. The bins on the far edges get very few, and the shape that emerges every time is a smooth, symmetric bell curve. That is the central limit theorem made visible. in wood and metal and gravity, the theorem says something almost astonishing about randomness. Take any random process, it doesn't matter what its underlying distribution looks like. It can be lopsided, strange, wildly asymmetric. Add up enough instances of it, and the total will follow a bell curve, always, without exception. The bell curve is not a property of any particular kind of randomness. It's a law that all randomness eventually obeys when you look at enough of it together. I find this almost unreasonably beautiful. The world is full of different kinds of randomness, processes that have nothing obvious in common, distributions shaped in 100 different ways, and yet they all converge on the same shape when you add enough of them. The bell curve is waiting for every random process, the way a river is waiting for every raindrop. The history of this result traces back to Abraham de Moivre, a French Huguenot refugee living in London in the early 1700s. So poor, he tutored students in coffee houses, who first noticed the bell shape while grinding through calculations about coin tosses in 1733. He thought it was a computational trick. It was a universal law. It was Laplace who understood its true generality. And it was Gauss, Carl Friedrich Gauss, the prince of mathematicians, born the son of a bricklayer in 1777, who made the bell curve immortal. Gauss did it by finding a lost asteroid. In 1801, the Italian astronomer Giuseppe Piazzi had spotted a small object moving across the sky, what we now know as the dwarf planet Ceres, made a handful of observations before it disappeared behind the sun, and lost it. Other mathematicians tried to predict where it would reappear. They failed. Gauss, using a statistical method he called the method of least squares, modeled the random errors in Piazzi's telescope measurements as a normal distribution, and worked backward to the most probable orbit. He told astronomers exactly where to look. They pointed their instruments there, and there it was. The bell curve had found a lost world. And here's why the normal distribution works so perfectly for errors in measurement. Any observation you make accumulates tiny random mistakes from dozens of independent sources, minute trembles in the instrument, small fluctuations in temperature, imprecision in the observer's eye. Each source of error is random in its own particular way, but add them all up, and by the Central Limit Theorem, the total error must follow a bell curve. The normal distribution is called normal because it's what you inevitably get when many small independent random influences combine, and the universe is absolutely full of those situations. Now, here's where probability touches something almost philosophical. Around 1827, a Scottish botanist named Robert Brown was looking through a microscope at pollen grains suspended in still water. They were moving, jiggling constantly, shifting in tiny, unpredictable directions, even though nothing was disturbing the water. He tried dead organic matter. It still moved. He tried particles of glass and metal. They moved too. Whatever was causing this, it wasn't life. For nearly 80 years, nobody could explain it. And then in 1905, a 26-year-old patent examiner in Bern Switzerland named Albert Einstein sat down and worked it out. Einstein said, the pollen grains are being hit constantly from all sides by water molecules. Individual water molecules are far too small to see, but there are unimaginably many of them, and they're moving randomly in every direction. Most of the time, collisions roughly balance out, but occasionally, by pure chance, one side gets hit slightly harder, and the grain lurches in that direction. Then from another direction, then another. The path it traces is completely random, each step independent of the one before it. No memory, no preferred direction. Pure chance, accumulating step by step into a visible wandering path. This is a random walk. And Einstein's equation wasn't just beautiful, it was the first decisive scientific evidence that atoms actually exist. The random walk mathematics predicted exactly how far a pollen grain should drift over time. And when those predictions were confirmed experimentally, the debate over whether atoms were real was essentially over. You can't see atoms, but you can see their statistical fingerprint. You can see what a trillion random collisions look like when they pile up into a visible wobble. And the precise relationship between time and drift follows a law. How far you've wandered grows with the square root of how long you've been walking. 100 random steps take you roughly 10 steps from where you started. 10,000 steps, roughly 100 away. Even pure chaos has a geometry. Let me shift gears now and tell you about a difficult, combative Russian mathematician who used probability to analyze poetry. Andrei Markov was born in 1856 in Ryazan, Russia. He spent his career at St. Petersburg, and he was, by all accounts, not an easy man to be around, argumentative, if yes, more interested in being correct than agreeable. He formally excommunicated himself from the Orthodox Church in protest when it excommunicated Tolstoy, which is the kind of biographical detail that tells you everything about a person in a single sentence. In 1913, Markov sat down with 20,000 letters from Pushkin's verse novel Eugene Onegin and recorded whether each letter was a vowel or a consonant. Then he asked, does the probability of the next letter being a vowel depend on what the letter before it was? Yes, of course it does. And Markov formalized this into what we now call a Markov chain, a probabilistic process where each next state depends only on the current state, not on the whole history of how you arrived there. The past doesn't matter, only where you are now. That single property, memorylessness, turns out to describe an astonishing range of real processes, weather patterns, molecules bouncing in a gas. The original PageRank algorithm that Google used to rank websites, which imagined a random user clicking links indefinitely, never with a destination, and asked where they'd spend most of their time. A Markov chain, the entire foundation of early internet search, in a direct line from a Russian professor reading 19th century poetry. And before I bring all of this together, one more piece. And this one I love precisely because it is simultaneously morbid and deeply funny. In 1898, A statistician named Ladislaus Bortkiewicz published a careful study of how many soldiers in 14 Prussian cavalry corps had been killed by horse kicks across 20 years of army records. Horse kicks are statistically ideal, rare enough to be interesting, but common enough across many corps and years to have a stable average rate. Bortkiewicz used these records to illustrate a distribution the French mathematician Siméon Denis Poisson had described in 1837, a model built for exactly this kind of situation. Rare events occurring independently over time at a roughly constant average rate. Phone calls arriving at a switchboard per hour. Radioactive particles decaying in a second. Typos per page in a long manuscript. The horse kick data fit the Poisson distribution so perfectly that it became one of the most famous data sets in the history of statistics. The message is almost darkly comic. Even death by horse kick has a formula. Even the most unpredictable individual catastrophe, viewed across enough instances, obeys a mathematical law. I find that strangely comforting. Not because individual tragedy is unimportant, of course it is. Terribly important to every person it touches, but because it means that chaos is not formless, that even in the most turbulent corners of reality, there is structure waiting to be found. Now, I want to bring all of these pieces together because there is a connection at the center of all of this that genuinely stopped me cold when I first understood it clearly. Think about everything we've covered. Kolmogorov's axioms, the Central Limit Theorem, the normal distribution and the lost asteroid, Brownian motion and the proof that atoms exist, Markov chains running from Pushkin to PageRank, the Poisson distribution of horse kicks in rare events. These feel like separate chapters, separate tools for separate problems. An orphan boy in Moscow builds a foundation. A French refugee in London notices a bell shape while calculating coin flips. A botanist in Scotland watches pollen jiggle. A combative professor reads poetry and thinks about fowls. A statistician in Germany counts military fatalities. But here's what's wild. All of these results, every single one of them, are consequences of Kolmogorov's three axioms, not loosely inspired by them, direct, logical descendants. The Central Limit Theorem can be proved from the axioms. Brownian motion is rigorously defined within the framework the axioms create. Markov chains are a specific kind of probability space that lives inside the structure. Those three rules describe the Moivre bell curve, Gauss's error distribution, Einstein's random walk equation, Poisson's distribution of rare events. All of it lives inside the architecture Kolmogorov built from three sentences that fit on a post-it note, and inside them, like a seed that contains a forest, is every probability calculation ever performed. The entire insurance industry built on the law of large numbers, which follows directly from Kolmogorov's framework, which says that over enough trials, averages reliably stabilize. Every weather forecast you have ever received, every clinical drug trial that decided whether a medicine worked, every spam filter, the mathematics behind how Netflix decides what to show you tonight, how your bank decides whether a transaction looks suspicious, how epidemiologists model how a disease spreads through a population. All of it is downstream of three statements written by a man raised by his aunt in Tambov, published quietly in 1933, the same year Hitler came to power, and the world was about to spend a decade demonstrating, among other things, that the randomness of history can be very brutal. Let that land softly. Probability has a spine now. It has architecture. It has a foundation as solid as geometry, built from as few assumptions as anything in mathematics. And within that foundation, the full extraordinary diversity of these results, bell curves and random walks and memoryless chains and rare event distributions, all fitting together with the coherence of something that was always waiting to be found. That is what Kolmogorov gave the world. Not a way to eliminate uncertainty, not a formula for the future, a rigorous, elegant, complete language for speaking honestly about what we know and what we don't. But here's where the story takes a turn. Nobody in 1933 could have predicted all of this mathematics, the axioms, the distributions, the theorems was built to describe randomness in the physical world. Dice, coin flips, pollen grains bouncing in water, soldiers and horses, and then, starting in the 1950s, people began asking a stranger and more ambitious question. What if you could use probability not just to describe uncertainty, but to learn from it? What if a machine could update its beliefs about the world the way Bayes said a rational mind should not just once, but continuously, automatically, growing more accurate with every piece of new evidence it encountered? What if probability wasn't just a language for measuring randomness, but an engine for something that looks from the outside a great deal like intelligence? The answer started arriving in 1948. Not all at once, more like a quiet avalanche. The kind where you don't notice it's moving until you're suddenly standing somewhere completely different from where you started. Claude Shannon was working at Bell Laboratories in New Jersey in the years just after World War II, and by all accounts, he was one of the more unusual people to ever walk those hallways. He juggled, he rode a unicycle through the corridors. He'd built a mechanical mouse he called Theseus that could navigate a maze, and he watched it find its way around corners with a private delight that his colleagues didn't always know how to categorize. And in 1948, this juggling, unicycle riding, maze, mouse building genius published a paper called A Mathematical Theory of Communication that quietly reorganized the intellectual foundations of the modern world. The thing Shannon figured out, and I want to slow down here, because this is one of the most elegant ideas in the history of science, is that information and probability are the same thing, not related, not analogous, the same thing. Here's the intuition. If I tell you the sun rose this morning, you already expected that the message carries almost no information. If I tell you the sun didn't rise this morning, that message would be staggering. It would carry an enormous amount of information, precisely because it told you something you had no reason to expect. Shannon formalized this. The information content of a message is tied to its probability. Rare events carry a lot of information when they happen. Expected events carry almost none. And the average information content of a whole system, what Shannon called entropy, borrowing the word from thermodynamics, is a probability calculation. You weight each possible message by how likely it is, multiply by how surprising it would be, and add it all up. What that means is that information is not a property of the message itself. It's a property of surprise, of the gap between your expectations and reality. Shannon showed that uncertainty and information are the same coin, viewed from different sides. That one idea became the mathematical foundation for every piece of digital communication on Earth. Every phone call, every compressed image, every streaming video, all of it flows through Shannon's entropy formula. The entire digital infrastructure of civilization is probability in disguise. And then people started asking, what if you could teach a machine to get better at probability? What if you could build something that updates its beliefs the way Bayes said a rational mind should continuously, automatically, growing more accurate with every piece of new evidence? And here is the historical puzzle that most people don't know. One of the very first people to actually do this wasn't building a product or running a company. He was cracking a code in the middle of a war to keep millions of people alive. Alan Turing was 30 years old in 1942, working in a nondescript building called Hut 8 at Bletchley Park in the English countryside, surrounded by mathematicians who had been quietly recruited to break Nazi Germany's encryption systems. Turing was, by most accounts, not an easy person to know. He cycled to work in a gas mask to protect against hay fever. He chained his tea mug to the radiator so no one could steal it. He reportedly buried silver bars in the woods during the war against the possibility of an invasion, then forgot where he'd put them. But what he did with mathematics in those years was, and I don't think this is an overstatement, arguably the most consequential application of probability in the history of human conflict. He developed a Bayesian method, a system for systematically updating probabilities that let the code breakers incrementally narrow down the settings of the German Enigma cipher machines. Every intercepted message added a little more evidence. Every piece of evidence updated the probability distribution, and when the probability crossed a certain threshold, they had the key. Historians estimate that Turing's methods shortened the war in Europe by somewhere between 2 and 4 years. Conditional probability, applied carefully, may have saved tens of millions of lives. Let that land for a moment. Not a theorem in a journal, not a tool built for profit, a probability calculation run by hand in a cold building in England, reshaping the outcome of the deadliest conflict in human history. The leap from Bletchley Park to modern machine learning is enormous in scale, but surprisingly short in concept. The first commercial machines to use Bayesian logic were not glamorous. In the late 1980s and early 90s, the most common application was spam filters. A naive Bayes classifier, the simplest version of this kind of system, works by looking at the words in an email and computing conditional probabilities. Given that this message contains phrases like wire transfer and confidential offer, what is the probability it's spam. The machine doesn't know the answer in advance. It learns from thousands of labeled examples, uses Bayes' theorem to update its estimates, and by the time it's seen enough data, it has absorbed something real about the structure of human behavior. Not because anyone programmed in rules, because it learned the statistics. That same architecture, scaled up and made more sophisticated, became recommendation engines, medical diagnosis systems, risk assessment algorithms. Every time a streaming service tells you what to watch next, or a hospital computer flags a patient as high risk, some version of this logic is running. Compute probabilities, update on new evidence, decide based on what the numbers say is most likely. The step from here to neural networks is shorter than it looks. A neural network is, at its mathematical core, a machine that learns to estimate probabilities by adjusting millions of small parameters until its estimates match the patterns in the training data. The process is called stochastic gradient descent. You adjust parameters a little in the direction that reduces error. Repeat millions of times on randomly sampled batches, and eventually the machine gets good at its job. Stochastic means random. Gradient means you're following the slope of the probability landscape. And the function at the output of every neural network called softmax converts raw scores into a probability distribution that sums to 1. The machine saying, given everything I have processed, here is my best estimate of what comes next. Now, here is where this story becomes something I think deserves a very long pause. The most powerful language models in existence right now, systems that write essays, answer questions, hold conversations that feel disturbingly coherent, are at their mathematical foundation, doing one thing, predicting the next token. A token is a small piece of text, sometimes a word, sometimes part of a word. The model receives a sequence of text and computes a probability distribution over every possible next token. It picks one, appends it to the sequence, and runs again and again and again, one step at a time, one probability calculation at a time, until a paragraph exists where there was none. Picture it this way. When a language model writes a sentence, it is not thinking the way you think. It is standing in front of an enormous probability landscape. Every possible next word is a hill or a valley, and it picks its path through that landscape one step at a time, guided only by what the statistics of human language burned into its parameters during training. There is no voice in there deliberating. There is no mind weighing options, feeling the weight of a particular word. There is a computation, a probability, a sample from a distribution. And yet, here is the part nobody fully expected, and that I genuinely don't think we have absorbed. When you make that probability machine large enough and fast enough, and feed it enough human language, hundreds of billions of words, essentially the entire written output of civilization across centuries, something happens, something we do not have a satisfying explanation for. It starts to seem like it understands. It answers questions that require multi-step reasoning. It makes connections across fields it was never explicitly told to connect. It writes with something that feels like a point of view. It models other minds, yours, as you read its responses and adjusts what it says based on what you seem to need. And the gap between computing probabilities over word sequences and understanding language is either very small or very large. And we genuinely do not know which. This is not a technology question. It is a philosophy question. It might be the deepest question in the philosophy of mind. And we stumbled into it by building very sophisticated autocomplete. These machines exist right now. You may have spoken to one today, and the people who built them do not fully agree on what is happening inside them when they respond to you. That is not false modesty. That is an honest report from the frontier. All right, let's shift to somewhere even stranger. Max Born was a German physicist born in 1882 who spent most of his career in Göttingen, one of the most intellectually charged places on Earth in the early 20th century. Born was more a builder of communities than a lone genius. He drew brilliant students around him, and from that constellation came some of the most consequential physics anyone has ever done. In 1926, one of those students, Werner Heisenberg, had worked out the strange new mathematics of quantum mechanics. Beautiful, internally consistent, experimentally powerful, but nobody quite knew what the central mathematical object of the theory, called the wave function, actually meant physically. What piece of reality did this equation correspond to? Born proposed an answer that is almost shockingly simple. The wave function gives you probabilities. If you square its magnitude at any point in space, you get the probability of finding the particle there if you look, not its actual location, its probable location. Before measurement, the particle doesn't have a definite position. It has a probability distribution over possible positions. Measurement collapses that distribution to a single value, and that value is random, governed by the probabilities the wave function encodes. This is the Born rule. And what it means is that probability is not just a description of our ignorance about reality. The universe itself is fundamentally, irreducibly probabilistic at its smallest scale. The randomness goes all the way down. Albert Einstein could not accept this. He spent decades searching for what he called hidden variables, some deeper description of reality that would restore determinism, that would make God stop playing dice. As he put it, he believed the quantum randomness was a gap in human knowledge, not a feature of nature. In 1964, a physicist named John Bell, working at CERN in Geneva, a quiet, methodical man from Belfast who had a habit of revisiting questions everyone else considered closed, proved that Einstein was wrong. Bell constructed a mathematical inequality that any hidden variable theory would have to satisfy, then showed that quantum mechanics predicts correlations that violate that inequality. Experiments confirmed it. The universe matches quantum mechanics, not any deterministic theory underneath it. The randomness is genuine. At the foundation of physics itself, the universe is a probability machine, which is, when you let yourself feel the full weight of it, kind of breathtaking. Now let's come back to the human scale, because probability has also shaped the world we actually inhabit in ways that are sometimes wonderful and sometimes catastrophic. In the early 2000s, a mathematician named David Lee, trained in China, then working on Wall Street, developed a formula called the Gaussian copula, used to model the probability that groups of mortgage loans would default at the same time. The formula was adopted across Wall Street almost overnight. Banks used it to price enormous bundles of home loans being sold to investors around the world. The formula said the risk was manageable. The assumption buried in it was that mortgage defaults were not very correlated with each other. If one homeowner in Ohio defaulted, it didn't say much about what a homeowner in Florida would do. The defaults were treated as approximately independent events. They were not independent. When the housing market began to collapse in 2006 and 2007, defaults cascaded simultaneously across the entire country. The correlations the model treated as small turned out to be enormous. The tail risks the formula had declared essentially impossible happened all at once. And the financial crisis of 2008, the worst global economic disaster since the 1930s, was, in a very real sense, a failure of probability, or more precisely, a failure of people who used the probability model without fully understanding its assumptions, and without honestly asking what would happen if those assumptions were wrong. A probability model is only as good as the assumptions underneath it, and assumptions can be catastrophically wrong. Medicine learned a version of this lesson too. The 20th century brought clinical trials, p-values, evidence-based medicine tools that have saved countless lives, but a disturbing fraction of published scientific results, in some fields estimated at nearly half, cannot be reproduced when someone runs the same experiment again. And a large part of the cause is a misunderstanding of what a p-value actually means. When thousands of researchers are running experiments and only publishing the ones where the result clears a threshold, you get a systematic bias. The experiments that found nothing disappear into file drawers. The coincidences get published, and slowly the literature fills with findings that are, in many cases, just the noise of probability behaving like probability. There's something almost poignant about this. If you sit with it, the tools built to protect science from fooling itself became, at scale, a mechanism for science to fool itself systematically, not through dishonesty, through a gap between what the math actually says and what the culture assumed it said. Probability, it turns out, is harder than it looks, even for people who work with it every day. All of this, the language models, the collapsing markets, the quantum particles refusing definite positions, the scientific results that don't hold on the second look, comes back to the same underlying truth. Probability is no longer just a mathematical tool we reach for when we need it. It is the infrastructure the modern world runs on. It is the substance of the machines we talk to, the structure of the markets we depend on, the literal behavior of matter at the scale of atoms. We live inside a probability machine, most of us, most of the time, without quite noticing it. And I think there is something worth sitting with in that something that lives somewhere between awe and unease, depending on the day and on what you happen to be thinking about. But all of this, the machines, the markets, the medicine, the atoms rests on a question that mathematicians have been arguing about for 300 years, and they still haven't settled it. What is probability? Is it a property of the world, or is it a property of our ignorance about the world? And does the answer matter? The question sounds almost too abstract to matter. Is probability a property of the world, or a property of our ignorance about the world? But here's the thing, if you care at all about any of the things we've been tracing tonight, the answer changes everything. And the honest, slightly uncomfortable news is that some of the sharpest minds in 300 years of intellectual history have been fighting about this exact question, and they have not settled it. Let me take you to two different places at almost the same moment in time to show you what the two sides actually look like. The first place is Hull, England, in the middle of the 19th century. A man named John Venn was born there in 1834. And yes, if you've seen those overlapping circles that diagrams use to show what two groups share, that's him. But Venn was more than a visual aid. He was a logician and a careful philosopher of probability. And in 1866, he published a book called The Logic of Chance that staked out what we'd now call the frequentist interpretation with unusual clarity and confidence. Venn also built his own pipe organs in his spare time, apparently out of sheer restlessness, and constructed a mechanical bowling machine that could deliver cricket balls at a consistent speed and trajectory. Whether this passion for mechanical repeatability bled into his philosophy, I genuinely cannot say, but it feels like it might have. His argument, stripped to its core, was this: probability is not something that lives inside your head. It is not a feeling about what might happen. It is measurable, repeatable, objective. The probability of a coin landing heads is 50%, because if you flip that coin a very large number of times, heads will come up about half the time. Probability is the long-run frequency, the limit that the ratio of favorable outcomes approaches as the number of trials goes to infinity. There's something deeply reassuring about this, something almost austere in how scientific it feels. Probability becomes a fact about the world that you can verify, at least in principle, not a mood or a hunch or a guess, a real feature of things. But the problems with this view come at you from several angles at once. Most of the probabilities we actually care about in ordinary life are not about repeatable experiments. When a weather forecast tells you there's a 70% chance of rain tomorrow, it is not describing a frequency. Tomorrow is not going to happen 100 times. It will happen once. When a doctor estimates an 80% chance that a surgery will succeed, she is not describing a series of identical operations under identical conditions, because no two patients are identical. When a geologist estimates the probability that a particular fault will rupture in the next 50 years. Well, there is no series of identical 50-year windows to compare against. The strict frequentist answer to this is to say those are not formal probability statements. They are hedged predictions, useful approximations, but not probability in the rigorous sense, which is fair, technically, but it sidesteps most of the things we actually need probability to help us with. And there is a deeper problem, one that I think is genuinely vertiginous once you see it. The long-run frequency is a mathematical idealization. You cannot actually flip a coin infinitely many times. The limit is imagined, not measured. And in classical physics, if you knew the precise initial conditions of a coin toss, the force, the angle, the air resistance, the exact surface it lands on, you would know the outcome every time. The 50% comes not from the coin or the air or the table. It comes from your ignorance of all those details, which means frequentist probability, examined carefully, starts to look a lot like exactly what the other side was arguing all along. So let's go to the other side. Cambridge, England, 1926. A young philosopher named Frank Ramsey, he was 23 years old at the time, working from a study that apparently required visitors to navigate stacked columns of journals and textbooks just to find a place to sit, was writing a paper called Truth and Probability that would quietly reshape how careful thinkers understood the whole enterprise. Ramsey was one of those people who made everyone around him feel gently outpaced. He read German, French, and Russian without much effort. He was close friends with Wittgenstein, the century's most demanding philosopher, and reportedly helped improve the Tractatus Logico-Philosophicus, which Wittgenstein considered nearly impossible to translate and Ramsey apparently found merely difficult. He co-founded decision theory while still in his early 20s, and by all accounts, he was very good company, warm and funny in ways that brilliant people are sometimes not. I find myself wanting to have had that conversation, the one where Ramsey explains something in an hour that would take anyone else a semester. What Ramsey argued was this: probability is a measure of your degree of belief, not a frequency in the world, not a physical property of anything, a representation of how strongly you expect something to happen, made precise by asking what bets you'd be willing to accept at what odds. If I'm 70% confident it will rain tomorrow, that means in Ramsey's framework that I'd accept a bet where I win 30 cents if it doesn't rain and lose 70 cents if it does. My confidence is operationalized through my willingness to gamble. Probability becomes personal, subjective, interna, a property not of coins or weather systems or surgical procedures, but of minds reasoning carefully about them. And here is what's wild about this. It doesn't make probability arbitrary. Ramsey showed that beliefs expressed this way must satisfy the axioms of probability, the same rules that Kolmogorov would later formalize, or they will be structurally incoherent. If your degrees of belief violate those rules, someone can construct a sequence of bets that guarantees they'll win money from you, no matter what happens. The Dutch book argument, it's called Irrational belief structures aren't just philosophically untidy, they're provably exploitable. Frank Ramsey died in 1930. He was 26 years old. Liver disease, most likely, though the exact cause was never entirely clear. A Cambridge journal called him, in its obituary, perhaps the most remarkable man Cambridge had produced in a generation. He had at minimum 4 more decades of work in him, and we don't have it. That's one of the losses in the history of mathematics and philosophy that I can never quite make peace with. His ideas were sharpened and radicalized by a brilliant Italian statistician named Bruno De Finetti, born in 1906, who went further than Ramsey had dared to go. De Finetti opened his 2-volume textbook on probability with a sentence in capital letters that has haunted everyone who has read it. Probability does not exist. Not probability is personal. Not probability is uncertain. Not probability is hard to pin down. Probability does not exist. His argument was precise. Probability is a property of our models, our minds, our expectations, not a property of the world. The world happens. It does not arrive with probabilities attached to it. Probabilities are the way rational minds represent their uncertainty about what the world is going to do next. And when the event occurs, the probability was not confirmed or disconfirmed. The event simply occurred. The probability was always ours, always internal, not out there. I've thought about this position for a long time, and I still find it simultaneously strange and impossible to dismiss. But here's what makes De Finetti's view more than just a provocation. He also showed that if two people start with different beliefs but update them consistently on the same evidence using Bayes' theorem, they will converge. The subjectivity washes out, the prior fades, the data dominates. You and I might start with very different estimates of whether a treatment works, observe the same clinical results, and end up in essentially the same place, provided we're both reasoning honestly and carefully. Bayesian subjectivity is not permanent. It's the honest acknowledgement that you have to start somewhere, that the first belief exists before the first data point, and that this is not a flaw. It is simply the condition of being a finite mind entering an uncertain world. Now here's the question that should be building in the background of all of this. Which of these interpretations is correct? And the answer that keeps returning to me after sitting with both for a long time is that the question might not have a single answer. The two interpretations are not two wrong descriptions of one thing. They may be two correct descriptions of different things. When we're talking about a coin, a radioactive atom, the spin of an electron, when we're in the domain of repeatable physical processes, the frequentist intuition captures something that feels genuinely real. There is a sense in which the coin's 50% is a fact about coins and physics, not just a state of mind. The world has structure. That structure has regularities. Those regularities are probability. But when we're talking about the probability that a specific patient will survive, that a particular company will succeed or fail, that a given fault line will rupture in the next century when we're in the domain of one-time events in complex systems. The Bayesian interpretation is the only one that's even grammatically coherent. There is no series of identical trials. There is only your best current estimate, grounded in everything you know, open to revision as things unfold. The philosopher Karl Popper, who spent most of his career in London and died in 1994, still arguing about almost everything, proposed a third option worth pausing on. Probability is neither frequency nor degree of belief. It's a physical tendency, a propensity. A loaded die has a propensity to fall on certain faces more often than others. That propensity is a property of the physical system itself, of the die and the throw and the surface, not of our ignorance about it. Probability becomes something like force, a real feature of the world that physical systems carry, whether or not anyone is watching or counting. The propensity interpretation runs into its own difficulties. It's not entirely clear how you measure a propensity except by observing its frequencies, which brings us back around. And for quantum mechanics, where the randomness appears to be genuinely irreducible, no hidden mechanism underneath, no deeper level of description, just pure indeterminacy. At the foundation, the propensity view has appeal, but also a kind of thinness. What is the physical carrier of a quantum propensity? Where does it live? That question, what carries quantum probability, what makes it real, is one of the genuinely open problems at the seam between physics and philosophy. Open, not because people haven't tried, open because the people who have tried most carefully have concluded that the honest answer is still not in. There's something I want to sit with here before we land. Every single thing we traced tonight has lived inside this unresolved argument. Bernoulli's law of large numbers was about how frequencies stabilize over time, frequentist in its bones. Bayes' theorem was about updating beliefs in the face of new evidence, Bayesian through and through. Shannon's entropy lived ambiguously between both interpretations, and Shannon himself did not try to resolve it. Turing's code-breaking at Bletchley was Bayesian in its structure. Begin with a pusher, accumulate evidence, act when the posterior crosses a threshold. The financial models that failed in 2008 were frequentist in spirit, calibrated against historical data, treating observed patterns as stable features of a world that turned out to be doing something new. And the born rule in quantum mechanics, the randomness at the very bottom of physical reality, is still philosophically disputed 3 generations after Max Born wrote it down. 300 years. Some of the most brilliant thinkers in human history. And the consensus is we know how to use probability. We have built extraordinary things with it. We have saved lives with it, cracked ciphers with it, mapped the structure of matter with it, and we still do not fully agree on what it is. Here's what I find beautiful about that. When I let myself, probability is not a simple tool we found lying around and picked up. It is an honest reckoning with what it means to be a finite mind in an uncertain world. Every probability estimate you've ever formed, every guess, every risk you've weighed, every forecast you've trusted or doubted is a small act of intellectual honesty. You are admitting that you don't know what will happen. You are admitting the future is not in your hands. And rather than pretending otherwise, you are doing the hard work of reasoning as carefully as you can across the gap between what you know and what will turn out to be true. That act reasoning carefully under uncertainty, rather than manufacturing a false certainty, is what the entire apparatus of modern probability was built to honor. From Pascal's problem of the unfinished game to Bayes' minister quietly updating his beliefs in the face of evidence, to the error bars on a medical study, to the confidence intervals in a physicist's notebook, to the probability distributions inside a language model predicting the next word. All of it is the same gesture. The refusal to pretend you know more than you do. The discipline of saying, here is my best current estimate. Here is how wrong I might be. And here is what it would take to change my mind. We traced a very long arc tonight. There was a mathematician in 17th century France, sitting by candlelight, trying to figure out how to divide a gambling stake fairly. There was a minister in 18th century England, writing a paper about updating beliefs in the face of evidence. A paper almost no one read for 200 years. There was a Swiss mathematician proving that large samples converge on truth. A German physicist staking out the claim that the universe is irreducibly random at the bottom. An American building mechanical mice and juggling in hallways, realizing that surprise and information are the same thing. A British mathematician in a wartime hut, turning conditional probability into a weapon against an empire. Each of them was solving a different problem. Each of them was working in a different century, a different country, a different field, but they were all circling the same center. The world is uncertain. We are finite. And the gap between those two facts is where careful thinking lives. You've been carrying all of this with you tonight. The long arc from dice to atoms to machines that generate language one probable word at a time. The quiet revolution of a theorem that turned evidence into updated belief. The wave function that says the universe doesn't commit to a definite value until you look. The financial formula that worked beautifully until the world changed and showed the formula its limits. It's a lot. You don't need to hold it all in sharp focus. The ideas will settle where they settle. And the ones that want to come back to you will come back. Somewhere in the background right now. Probability is running in every system you're part of. The rhythm of your breathing follows a distribution. The temperature in the room you're in has a variance. The neural patterns that generate dreams, if the neuroscience is even approximately right, are themselves a kind of sampling process. Your brain drawing from a space of possible experiences weighted by what it knows and fears and remembers and hopes for. You are, in a sense that is more literal than it might sound, a probability machine falling asleep inside a larger probability machine, embedded in a universe that has not yet decided whether its fundamental randomness is a property of the world or a property of the gap between what the world is and what we can know about it. Nobody has settled that question. Not in 300 years. Not yet. And I find that somehow the most restful thought I can offer you. Some questions are so deep and so honestly difficult that the right response is not an answer. It's something more like gratitude. Gratitude that the world is complicated enough to sustain 3 centuries of brilliant argument without yielding. Gratitude that the question is still open, which means the conversation is still happening, which means we are still in the middle of something rather than at the end. You don't need to resolve it tonight. The probability calculations will keep running with or without your supervision. The electrons will keep declining to settle into definite positions until they're measured. The models will keep learning. The Bayesians and the frequentists will keep writing papers at each other, and you can rest. The uncertainty will wait for you, patient as it always is, exactly where you left it,